All right, so we're doing our final recitation of the semester. And I want to spend most of today looking at, come on. I want to spend most of the day looking at integration and what we do with integration. And really, I've been referring to these things called the four principles of integration. And if you abide by these four guidelines, you're usually going to get your integration problems correct. So the first and most important one is the syntax. Generally speaking, whatever you're ending your integration with, it's supposed to be a scalar, not a vector, unless you're really specifically working in the circumstance where you've got some velocity or acceleration of a moving particle. So what that means is that make sure that your cross products are coming out to be vectors, cross products are vectors, dot products are scalars, and an integral is a sum of these things. And whatever you're doing should work out to finally be some scalar. So make sure the syntax makes sense. Also, you've got a bit of a concern about dimension. And when I say dimension, what I mean is the dimension of the underlying region or surface or curve or whatever that you're integrating over. What I refer to as the size dimensions, this is the number of dimensions that it feels like your space, your integration domain is. So for example, curves, curves have length. You talk about how big a curve is in terms of its length, and the length is a one-dimensional size. Surfaces have area, which is a two-dimensional size, and solids have volume, which is three-dimensional. Now, the number of integrals you have to do when you iterate it, that's got to be the same number as the number of size dimensions of your space, and that's also the same number as the single variable differentials you have with the integrated integral. So for curves, that's dt. For surfaces, that's usually du, dv, or perhaps dx, dy, etc. And the number of variables you have to integrate, those all have to be the same number, and those tell you the dimensions of the integral and of the space you're working with. We also talk about what Dr. Roberts and I refer to as the stretch factor. And that's also known as the Jacobian. And this is how much change has to happen in your space when you are, as you're integrating. And that is usually going to be a derivative of the parameterization of your curves or your surface in some respect, and it should approximate some kind of an area. So for example, for curves, that's approximated by the magnitude of the velocity, magnitude r prime. For surfaces, that's usually going to be the cross product, the absolute value of the cross product of RU cross RV, and that's going to tell you approximately the area of a very small parallelogram patch on your surface. And finally, the fourth principle is this thing called the fundamental theorem of calculus. And there are several different versions of this that we've seen at this point for different contexts. And what it all basically boils down to is if you're taking an integral and you're taking the integral of some kind of derivative, then that's the same thing as undoing one of those integrals. That's what I mean by when I say an n-1th integral. You're undoing one of those integrals, and then you're integrating on the boundary of the region. Either that means the boundary of the surface or the surface of a solid. And by that logic, that does in fact mean that these first two fundamental theorems of calculus that I'm referring to here, the first one is the FTC from all the way back from Calc 1, and the second one is as we know it now, as the fundamental theorem for line integration. So let's do an example of this. We want to evaluate the integral x ds over some curve c, and c is going to be the arc of the parabola y equals x squared from 0, 0 to 1, 1. Now it's always, it's always a good idea to try drawing the region you're working with here. So in this case, when we draw it, I'm going to try drawing this as straight as possible, even though I'm not a very good artist. Basically, this boils down to basically this. We know exactly what this looks like. It's this. I'm trying to make it look a little more like a parabola. We know it's going to be this arc of this parabola. This is c from 0, 0 to 1, 1. Now, in this case, we know that the integral. We're looking in this case at a scalar differential, as opposed to a vector field. Oh, sorry, not differential, excuse me. Scalar integrand. Now, when you parameterize this curve, the best way to parameterize it, I think, is using RT is t comma t squared. And where does that come from? That's just coming from if you set x to be equal to t, then y is equal to t squared, because that's, I mean, come on, that's the same thing as x squared in that case. So that'll work out exactly what you want it to. Some people actually write r of x instead of r of t for this exact reason. It doesn't matter. You can do it either way. Now, the formula we need in this case is this. Right? We know you're evaluating f along this curve, dt. Now, I'm leaving the stretch factor blank because maybe you don't remember what this is, but you know that it has to be only one integral because it's a curve, and you know that it's a it's a scalar differential and a scalar integrand. So you're summing up a bunch of scalars. So what's the stretch factor? Well, the stretch factor is going to be some kind of derivative of the parameterization, which means it's going to be some kind of r prime of t. That's got to get in there. But this clearly isn't it, because this is multiplying a scalar by a vector. So that's a vector. So that's going to come out to be a vector, which is not what we want. And you're not going to dot it either, because if you dot it, then that would mean you're dotting a scalar and a vector, and that can't happen either. But what you can do is take a magnitude. Now, that's the product of two scalars, and that's what you need. That's exactly it. So just abiding by these principles of integration will usually get you what you want. Now, in this case, r prime of t, that's not hard to calculate. R prime of t just comes out to 1 comma 2t. And in which case, the magnitude of r prime of t is the square root of 1 plus 4t squared. And finally, we just need to know what f of r of t is. Well, f of xy is just x is t, so that's just going to be t. So we're pretty much ready to answer this question at this point. X ds is the integral from, and in this case, it's going from 0 to 1, because t is starting at 0 and getting up to 1. X is going from 0 to 1. T is going from 0 to 1 because x is equal to t. And what you get is t times the square root of 1 plus 4t squared dt. And that's basically just your run-of-the-mill u substitution. In this case, we're going to let u equal 1 plus 4t squared. du is going to be, in that case, 8t dt. And when we used to have t going from 0 to 1, we now have to say that u is going from 1 to 5. Right? So u is going from 1 to 5. So that's going to give us integral from 1 to 5, changing the bounds of integration in this case, integral from 1 to 5 of the square root of u over 8 du. And that's the same thing as 1/12 u to the 3/2. Evaluated from u equals 1 to u equals 5, which comes out to 1/12 times 5 to the 3/2 minus 1. It's pretty much all there really is to it. So any questions so far? Yeah, the most important thing is to make sure that you remember what the formula is, or at least have enough intuition for integrals that you can reconstruct the formula, which is hard. I acknowledge that that's difficult, but once you can write out the formula and see what you really need, it makes everything else make a lot more sense. Okay, here's another example. What if you have the integral of over c of the function xy dx plus y squared dy plus yz dz, and c is this line segment. Now, it might not look it, but that's a vector field. We are, this is a kind of a vector field integral. And it's the vector field integral that, in this case, the vector field is f x, y, z is just x, y, I plus y squared j plus y, z, k. Okay, so that's about all that's really going on over there. Now, what about the, so now that we can see that, how are we going to go about solving this? Well, it's a vector field integral, and there are really three different strategies for this three-dimensional object. One of them involves, you can try adding an integral. And if you try adding an integral, well, the way you do that is with Stokes' theorem, right? This is the fourth principle of integration. You can add an integral by adding a derivative, and if you think about what that derivative has to be, there's really only one reasonable option. It has to be a cross product because you can't. It's not going to be divergence. It's either divergence or a cross product, and divergence wouldn't make a whole lot of sense in this case because divergence is really about spreading out over a three-dimensional area. Curl would be a little more reasonable. So that's the derivative that we're interested in, dot ds, and that's Stokes' theorem. But we can only do this if C is the boundary of some surface S. And it isn't. And you know that it isn't because C is a line segment, so that's not going to work. What if we tried removing an integral? You can do that too, using the fundamental theorem of line integrals, which says that if you take a line integral of a gradient, then that's the difference between f at the end and f at the start. Problem with this is this will only work. This will only work if you have that your vector field in question is in fact the gradient of something. Well, I don't know if it is or not, but let's find out. Well, if it were, you can test this a couple of different ways. You can see what the curl is, and if the curl is 0, then we're in business. But if it's not, then we can't do it. But if you don't remember what your three-dimensional test is, that's okay. You can just try doing it directly. You would need it to be the case that fxyz is the antiderivative of x, y, dx, which is just 1/2 x squared y plus some function g, y, z. And that means that if you differentiate this with respect to y, you get 1/2 x squared plus gy, gy, yz, and that has to be the same thing. That has to be the same thing as y squared. But we've got a problem now. But the problem that we run into in this case is the partial derivative of g with respect to y of this function of y and z, which can only depend on y and z. It can't depend on x. It can only depend on y and z. But it's equal to y squared minus 1/2 x squared, which patently depends on x. So that's contradictory. So no such potential function exists. This leaves us with only one option. We have to hit this with a direct approach. And the direct approach in this case just tells us that we have to find f of the parameterization along that curve, dotted with, and actually I'm not even going to say that, I'm just going to say dt on the other side. And if you forget your principles of integration, what does this have to be? Well, you're integrating along curve, so there's one variable integrating, because curves are one-dimensional, they have a length. What about the stretch factor? Well, the stretch factor, again, it's a derivative, and it's got to be a scalar. The only way for it to be a scalar, if this is a vector field up here, it has to be a dot product. So you dot it with the derivative of r of t. So you dot it with r prime of t. So what's r of t? Well, for the parameterization, for line segments, you can use this little trick. The trick is you can let r of t be equal to one value, in this case, or one vector, 1, 0, -1, which the line contains, or the line segment starts at, plus t times 3, 4, 2 minus 1, 0, -1. In other words, that's going to become 1 plus 2t, 4t, and and -1 plus 3t, which means r prime of t is then going to be, oh, sorry, let me make that a little more equal looking, 2, 4, 3. Now, meanwhile, you need to know what f of r of t is, and f of r of t, just plugging in these functions for x, y, and z in terms of t exactly as you see them. In this case, that means x times y. X times y is going to be 8t squared plus 4t I. J squared is going to be 16t squared. And then yz in the k direction is going to be 12t squared minus 4t. And I left out a j. Oops. And now you take the dot product. What does the dot product give you? The dot product is going to give you f of r of t dotted with r prime of t. That's 16t squared plus 8t plus 4 times 16 is going to be 64t squared plus 36t squared minus 12t. Now simplifying that down a little bit, 116t squared minus 4t. We're basically ready to solve the problem at this point. So we take the line integral, integral over cf dot dr, integral from 0 to 1. I forgot to mention that, by the way. This parameterization works for t going from 0 to 1. And if you don't believe me, just try it out. I mean, that's certainly a line segment because all the terms are linear. And if you plug in 0, you get 1, 0, -1. And you plug in 1, you get 3, 4, 2. So it's exactly what we want. Okay, so, and you plug in the new integrand that we just found. So that's 116t squared minus 4t dt. What's that going to become? 116 over 3 minus 2. Or if you prefer, you should prefer 110 over 3. And that's basically all that boils down to. So in this case, you really had no choice. We really had to use, we really had to use the direct approach. We didn't really have using the, we didn't really have using either Stokes' theorem or the fundamental theorem of line integrals. Neither of those were really options for us. Okay. Okay, so let's do another one. On the other hand, you could have, here's a vector field for you, and C is going to be this curve. Evaluate this line, this line integral. Again, you want to try asking yourself, okay, what are the options? The best thing you can do is you can ask yourself, can you remove an integral? you can add an integral or you can use the direct or brute force approach. To remove an integral, well, that means you need f to be the gradient of something. And the reason why that's true is because, again, by our principles of integration, you can remove an integral if the thing you're integrating is some kind of a derivative. This becomes f at the end minus f at the start. You can add an integral by taking the integral over c of f dot dr, and this is two-dimensional, so you would have to add it by using Green's theorem. Or you can use the direct approach. And you can only use Green's theorem, by the way, if C encloses and must enclose some region D. But you can play with this a little bit and notice that R of, oh, I forgot something important. T is going from 0 to 1. Now R of 0, you can just stare at that and you see that R of 0 is 0, 1. But R of 1, on the other hand, again, you can take a look at this and see that R of 1 is 1, 1. So it doesn't start and end at the same place, so it doesn't enclose a region. This isn't an option for us. The last thing we can try doing is the direct approach, which we just explored. F dot dr is always equal to the integral over, the integral from a to b of f of r of t, r prime of t, dt. Now that can be a very hard integral to do, and I'll let you know up front, this would be an extremely difficult integral to attempt to do this with. So we're not going to use that strategy here. I mean, in principle, you can do it, but it's really frickin' hard. And we're not going to go there. So we're going to try doing a different approach. You can't add an integral. And the direct approach is cruddy. So we're going to try removing an integral instead. And notice that del q del x is, actually, I'll write it this way. So we can use this strategy if qx minus py is equal to 0. What's qx? Qx in this case is, so qx in this case is going to be 8x cubed y minus 6x y squared and py, meanwhile, py is going to be 8x cubed y minus 6x y squared. Aha! These are the same. And because those are the same, you can hit this with the fundamental theorem of line integrals as soon as we find our potential function. So for that, we know that fxy is the antiderivative of 4x cubed y squared minus 2xy cubed dx, or in other words, x to the 4th y squared minus x squared y cubed plus some function g of y. And I don't know what that function is, but that's okay. We'll figure it out. We know that fy, xy, has to satisfy 2x to the 4th y minus 3x squared y squared plus g prime y. But that has to be the same thing as 2x to the 4th y minus 3x squared y squared plus plus 4y cubed. So if you give me a second to erase some stuff, the upshot of that is we now know what g prime of y is. G prime of y is going to be 4y cubed, and that makes g relatively easy to figure out. So give me a second. So we know that g prime, so 1 second. Upshot of all of this is we know that g prime of y is equal to 4y cubed, and that means g of y is equal to y to the fourth. So the actual function we want is fxy is x to the fourth y squared minus x squared y cubed plus y to the fourth. Our vector field is simply the gradient of this potential function we just found. So we just evaluate at the endpoints. We know what the endpoints are. We figured those out given our knowing that t is going from 0 to 1, which obviously is information that you need. f11 minus f00, which comes out to be 1 minus 1, or in this case, 0. And that's the gist behind how this kind of problem really works.